Okay, here we go. So this is chapter 11, section 1, and it deals with tests about a population mean. So now we're back to hypothesis tests. All right, so here's what we're going to be doing. What are we trying to accomplish with this test? We're trying to answer the question, is the mean mu for some parameter of a population, something we are interested in, a specified value? Is it more or less or different from that specified value? So it's kind of a yes or no question. There's no way for us to know the actual value for the entire population, but we can run a test based on our sample and be reasonably comfortable with our answer. How comfortable, you might say? That's where alpha comes in. We set alpha at a level that allows us to feel good about the decision we will be making. Usually alpha is set at 0.05, but it doesn't have to be. It can be more than that or less than that, depending on how sure you want to be. So inference about a population mean, mu, uses a t distribution. Remember, we learned about that in the last section, with n-1 degrees of freedom, except in the rare cases where the population standard deviation is known. So here is an example. In an earlier example somewhere, I don't know if we went through this or not, a company claimed to have developed a new AAA battery that lasts longer than its regular AAA batteries. Based on years of experience, they know their regular AAA batteries last for 30 hours on average of continuous use. So a simple random sample of 15 new batteries lasted an average of 33.9 hours with a standard deviation of 9.8 hours. Here is the data. Do these data give convincing evidence that the new batteries last longer on average? Use alpha equals 0.05. To find out, we must perform a significance test where our null hypothesis is that mu equals 30. The alternative mu is greater than 30, where mu is the true mean lifetime of the new deluxe AAA batteries. Okay, so checking our conditions. If our conditions are met, we're going to use a one-sample t-test, or on the calculator, just t-test. Conditions are the same as for a confidence interval. What are they? The data must be from a random sample or random assignment to treatments. In this case, they are from a random sample, stated in the problem. We can't sample more than 10% of our population if we're sampling without replacement, which we are. I think we can assume that 15 batteries is less than 10% of all the batteries. And n must be greater than or equal to 30, which in this case it's not, it's only 15, or we look at a graph. So here is a graph. Now you can see this is not really normal, but it doesn't have any strong skewness or outliers. It's pretty stretched out, but it looks okay, so we will proceed. So carrying out our test. The significance test, the test statistic measures in standardized units how far the sample result is from the parameter value specified by HO. So in this case, 30 hours. And here's the generic form for a test statistic. Here's in this particular case, because sigma is not known, we use t rather than z, and we use Sx, which is the standard deviation of the sample, instead of sigma. So t equals sample mean minus hypothesized mean for the population divided by the sample standard deviation divided by the square root of n. So in our example, here's how we calculate t. This is the sample mean. This is the hypothesized mean. Sample standard deviation, n was 15. That gives us 1.54. So what are we looking at here? So we're looking at a normal distribution where the mean, in this case, the mean is 0 because we have standardized. Okay, and the standard deviation is whatever that was. What is the standard deviation? 9.8 divided by the square root of 15. I didn't calculate that. And we want to know what is the probability that we get something in this shaded area. So you can see that's not that low. Okay, t equals 1.54. I think maybe that's because I probably used a normal distribution to come up with this picture. All right, so here's our calculations. On the calculator, once you have your t value, you do a second vars t CDF, lower in this case 1.54, upper 10,000 or just some really big number, degrees of freedom 14, and that gives us a p-value of 0.0729. All right, so actually going back here, I was wrong about this, so this makes sense. So we can see that it's not that unlikely. Or use t-test on the calculator, and in this case we would enter the data and let the calculator do all the work. Conclusion: because the p-value of 0.073, I rounded, is greater than alpha equals 0.05, we fail to reject the null hypothesis in favor of the alternatives. The new batteries, we don't have evidence to say that the new batteries last longer than the old ones. We do not have evidence that the new batteries have a longer life than the old ones. Okay, so that was a mistake on my part, but I don't want to do this again, so I'm just going to leave it there. All right, and just note, for a two-sided test, you would take your p-value and double it if you were doing a not equals. Okay, very quickly, the relationship between two-sided tests and confidence intervals is even stronger for means than for proportions because the standard error is used in both calculations. So for example, two-sided tests at the significance level alpha equals 0.05, they give similar information about the parameter. When the two-sided test rejects, let's see if I can move this up, yes I can, rejects the null hypothesis, the confidence interval will not contain the hypothesized value mu 0. When the two-sided test fails to reject, the confidence interval will contain the hypothesized value. All right, now, last topic here, paired data. You may recall matched pairs data from a long time ago. This is a similar idea. Comparing two observations on the same individual or one observation on two similar individuals or individuals that can be paired for some reason results in paired data. So compare by finding the differences in each pair by subtracting, and then use a one sample procedure to find the inference. So here's a couple of examples of that. We use paired data with each element is paired in the first set, 2 at 1 in the second set. And in this case, the mean of the difference is not the same thing as the difference of the means. So what am I talking about? Here is an example. Ultrasound is often used to treat soft tissue injuries. Okay, in an experiment, let me make this a little smaller so we can fit it in here. Okay, so in an experiment to investigate the effect of an ultrasound and stretch therapy on knee extension, range of motion was measured both before and after treatment for a sample of physical therapy patients. A subset of the data is given in this table. So here's there are 7 subjects, pre-treatment, post-treatment, difference. So rather than using this data at the top compared to this data at the bottom, which we would do in a 2-sample t-test, we're going to find each difference and do a 1-sample t-test with the difference, because it makes sense to compare subject 1's pre and post treatment for that patient, and the same thing for patient 2 and patient 3 and so on. Okay, so here are our hypotheses. Mu d equals 0, mu d is greater than 0. Okay, so we're saying mu d means the difference, the mean of the difference. So we find the mean of these differences, and we're saying that the mean will be 0, or that the mean will be greater than 0. Use a 1-sample t-test where each data element is the difference in the range of motion for each participant. So what does that look like? Here's our data, just kind of thrown up here. And so you could see it kind of looks like there is a difference because the yellow dots are all kind of moved over from the blue ones. And then when we look here, we can see this is where we're pairing. This person went from here to here and so on. Only one person went backwards. Everyone else went forward. Here's another example. Researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, etc. During one 2-day period, they took capsules containing normal caffeine. During another period, they took placebos. and the order in which they took the caffeine, the placebos, was randomized, and then they compared their depression levels before and after, or in each case. So here is the information. So here are the 11 subjects: depression, caffeine, caffeine with caffeine, depression without caffeine, and the difference. You can see actually all the differences except one are positive, so that would imply maybe there is a difference. So why did the researchers randomly assign the order in which the subjects received the placebo and caffeine? They wanted to be able to conclude that any statistically significant change is due to the treatments themselves and not some other variables. For example, suppose the caffeine was given to all the subjects during the 2-day period. What if the weather was nicer on one of those 2 days and the second day was raining? So that might have an effect. That's just one example. So by randomly assigning them to treatments, we normalize that kind of effect. Yep. Should help ensure that no other variable like weather is affecting the responses. Okay, so we have paired data again. So this time we're going to walk through all 4 steps of the process. So we want to test the hypotheses that the mean is no different versus the alternative that it's greater than 0, where mu d is the true mean difference. Placebo minus caffeine. Actually, I think this is backwards. It should be let me just change this here. This should be less than 0 because we think that the amount of depression would be negative. Placebo minus caffeine. We think there's going to be less depression with caffeine, I think. Okay. Let me do that one more time. Placebo minus caffeine is greater than 0. That's what we're hypothesizing. Okay, because no significance level is given, we'll use 0.05. So conditions. First 2, random. The researchers randomly assign the treatments, 10%. We aren't sampling, so it is not necessary to check that condition. And then for the normal large sample, we only had 11, so we do have to look at graphs. So we made a histogram, a box plot, and a normality normal probability plot. And you can read here that all of them seem okay. So we're going to proceed. So here we're going to put the data into list 1 and then use the calculator's t-test with the draw command. The test statistic t equals 3.53. The p-value is 0.0027, which is to the right of the area of t equals 0.353, and the degrees of freedom is 11 minus 1, or 10. Conclusion, because this is very, very small, smaller than 0.05, we reject HO, mu d equals 0. We do have convincing evidence that the true mean difference is positive for subjects like these. Notice we can only generalize to subjects like these because we did not randomly select our subjects from the population. Okay, using tests wisely. I think I'm going to skip this. You can read this on your own. So pause here and read. And same thing here. And that's it. So hopefully this is helpful.